Okay, so today we're going to talk about the ideas of finding volumes of solids. What we're going to do first of all is we're going to start off with kind of like a basic idea or a basic example of what's going on. So, imagine that I have, I don't know, something that maybe looks like a loaf of bread, for instance. So, if it kind of looks like this, and we're asked to find the volume of this guy right here. And so clearly you could see that at first this might be a little complicated looking. So what we want to do is the following. So these are kind of like the steps we're going to follow. We're going to say, look, to find the volume of this, we would need to find the area of the cross sections. And so what we're saying here is that we need to find a general formula for this. And so what we're saying as far as our cross sections go, hopefully you know what a cross section is. A cross section is, look, if I were to slice this, what shape would I see? And the shape I see, that's the cross sectional area I want to find. So you could see that if I were to slice this bread, I would see a cross section of that. So you might be wondering, well, why do we need to find area? So let's kind of take a step back and go with like the basics of what we've learned. So here's what we're going to do. So if I want the cross-sectional areas, what we're going to do is we're going to grab this and just slice this up. So if we then slice up the figure into n parts, which that's what our delta x is. Now, if you remember, you'll see where the delta x comes into play. If you remember when we were finding the area under the curve, we would first come up with a general formula where we would divide up the subinterval into n parts, which is a finite number, and then we'd find the area of each rectangle and we would add them up, and that was actually an estimate. So that's kind of where we're headed here. So what we do is we break this up into n parts, and we find the sums of the volumes of all pieces. We then have an approximation of volume. So in other words, what we're saying is, if I were to grab this guy and I were to slice it into a certain number of pieces, okay, so imagine if I were to grab this and slice it into, I don't know, 4 or 5 pieces, how would that look? If I were to do that and I sliced it up into 4 or 5 pieces, it would probably look something like this. So here's kind of, you know, I'm not the greatest artist in the world, so I'm just trying to kind of draw out what it would look like. So there would be one slice, and then another slice would kind of look like this, and then it would go up higher, and then we would slice these up into a bunch of pieces. And so what the problem becomes is when we generate a slice, or when we start slicing this up, so if I were to kind of draw another picture of what's going on here, so if I were to slice this up, if I have kind of this shape here, and I grab this bread and I slice it up, what happens is, what we're doing is we're finding the volume of this piece. Now, unfortunately, when we slice this up into finite pieces, there's going to be parts that we're going to miss it. So our approximation, or our volume, is actually going to be an approximation. So what do you notice? If I increase the number of slices I have for this guy, then I'm going to get a much better approximation of this. So in fact, what we could say is that, notice how as n approaches infinity, which these are the number of slices, we will have a better approximation of volume. And one comment I'll make here is that, well, if I'm making infinitely many slices, that will be, in fact, we'll have exact. So it'll be exact volume. So what we notice is the more we slice these up and we find the volume of each piece and we add them up, we start getting an approximation. So the more slices we have, the better approximation of volume of the sky. And if we have infinitely many slices, then we start getting the exact volume of this shape. And so if you notice the infinitely many slices, that's kind of getting us towards the definition of a definite integral. So what you're noticing is that the definite integral is also going to be used to help us find volumes. So let me define it, and then I'll show you where the motivation comes from. So here's what the definition of volume is. So the definition of volume says the following. It says, let S be a solid that lies between x equals to a and x equals to b. If the cross-sectional area of S in the plane P sub x through x and perpendicular to the x-axis is a of x. So let's be careful real quick. So what are we saying here? The cross sections that we're taking are going to be vertical cross sections. So what we're saying is our cross section is going to be perpendicular to the x-axis, which means if my cross sections that I'm taking are perpendicular to the x-axis, then we need to find the area of the cross section, and the area should be in terms of x. Okay, so what we're saying where, and of course where A is a continuous function, then the volume of S is V equals to the limit as n goes to infinity, summation from I equals 1 to n of A of x sub I star times delta x. And if you notice, what is this? This is volume, okay? Because what do we have here? Why is this the volume? This is the area of the cross-section times the thickness, which area of the base times the height. That's the volume, and I'm adding up infinitely many, which this, by definition of a definite integral, that becomes the same thing as what? The integral going from x equals a to b of a of x dx. So what this says here is, look, to find the volume of a solid, all we need to do is find the integral from the lower limit to the upper limit of the area of a generic cross section. Remember, I want to be able to cover all the cross sections. Now, why do I care about the area of the cross section? Well, the dx is still there, which is the volume, but remember, what happens when I divide something up into infinitely many subintervals? The thickness becomes so small where the area of that cross section does a good job approximating what the volume is. So think about it, for example, this way. If I said, this is a stack of papers, right? So I have a stack of papers here. Look at the thickness right there. If I said, find me the volume of this paper, what you would do is you'd say, look, if I slice these papers up into really, really thin pieces, which if you look at a singular paper, see this has almost no thickness. So what do you notice? The area of this paper is a good way of approximating the volume of this paper. So what do? If I take the area of this paper plus the area of the next set of papers plus the area of the next set of papers, and if I keep adding these areas up, eventually all those areas I've added is going to give me that thickness, which then all those cross-sectional areas added together give me the volume of this. So that's kind of what's going on here. Now look, the paper that I just showed you had some thickness. Now imagine if we divide it up even into more pieces. So basically what we're doing is we're slicing these pieces right here into so many, we're slicing the solid into such small subintervals where they're infinitely many, where the cross-sectional area kind of acts as the volume. So if I take the cross-sectional areas and I add them all up starting from A and going to B, that will give me the volume of the solid. So what we notice here is that, look, when you draw your solid, you first want to take the cross-sectional area. And then when you come up with a generic formula for the cross-sectional area, then you're ready to find basically the volume of that. And so that's what we're going after. So one comment I want to make is the following before we do a couple of examples. So when using the formula v equals the integral from a to b, a of x dx, remember that remember that a of x is the area of a moving cross section obtained by slicing through x perpendicular to x-axis. Now, what if I gave you something like this? For the volume equals the integral from a to b, a of y dy, that means my cross sections are horizontal. I'm going perpendicular to the y-axis. So this is basically cross sections by slicing through y perpendicular to y-axis. So if I see, you'd have to basically decide, hey, which kind of cross-section do I want to take? Perpendicular to the x-axis or the y-axis? And sometimes one would give you a much better shape that you'd find the area of rather than the other. And for the most part, I think we're going to be dealing with circles. So you want to go the way where you're going to get a cross-section that's easy to find the area of. Just remember, for this one, the area has to be in terms of y because we're integrating with respect to y, and then my lower and upper limits have to be y values, okay? So with that said, just to kind of generalize what we want to do, the volume of a solid is obtained by finding the area of a generic cross-section. We integrate from the lower limit to the upper limit, and then that should basically get us the volume. Okay, so hopefully the motivation makes sense as to why this turns into that, because after all, area of the base times the height, that's the volume. And if it's infinitely many, I'm adding up a bunch of these volumes, and this by definition becomes into the integral. So remember, our sample points become just x. How come? Because the subinterval becomes so small where my subintervals, like if I have x sub I minus 1 and x sub I, this subinterval becomes so small where x sub I minus 1 and x sub I are practically become the same x value, and that's why this just becomes a of x. So it's a kind of nice way of getting around it. So let's look at our examples. So the first example is going to be to show that the volume of a sphere is v equals to 4/3 pi r cubed. Okay, so, and of course we're assuming that the sphere has a radius of r. So if you remember in geometry, you're kind of forced to memorize this volume. And once again, you guys know I'm not a big fan of memorizing things. So we'll actually be able to find the volume of the sphere without memorizing the formula. We could actually derive it using calculus. So here's what we're doing. Since they don't tell us where the sphere is located, we're better off drawing the sphere with its center at the origin. So here's our sphere. So if you look at this, what do you notice? If I were to take a cross section, okay, if I take a cross section, let's see which way would work. If I take horizontal cross sections, I get circles, which that's nice. And if I take vertical cross sections, I'll also get circles. So notice in this case, it doesn't matter. And by the way, this is going to be r, negative r, right? Because this has a radius of r. So it doesn't matter what kind of cross section we take. So I'm going to take cross sections perpendicular to the x-axis. So if I take a cross section, a single cross section is going to look like this. Okay, so what do I want to do? I want to find a generic formula for this guy, for the circle, which means if I want to find the generic formula for the circle, all I need to do is I need to find the area of the circle with respect to x. So let's call this value here x. Okay, so what I want to know is that this x value, how would I find the area of the circle? And so here's what we want. We want the volume, which is the integral from negative r to r of a of x dx. Okay, and so better yet, we could say, look, since this is symmetric with respect to the y-axis, aren't we better off? Or we could say the volume from 0 to r of a of x dx, and I could just double it. So this would also get the job done. Okay, so whichever one you want to do, it doesn't matter. But what I need to do is I need to come up with a way of finding a generic equation for this circle, which is in terms of x. So basically I'm saying if this is x, which x is going to range from where? 0 to r, anywhere there, how would I find the area of the circle? Well, what we know is that the area of a circle obviously is pi times the radius squared. Okay, and so how would I find the radius of the circle? Well, what's the good news? Notice how the radius of the circle starts where? From the x-axis and ends on this circle. And see, we already know how to find the equation of a circle centered at the origin with a radius of r. So what I notice is that we could say, look, if I were to draw this separately, I would say, notice how my cross section, which this is the cross section, um, ends up giving me the area of that, the radius of that circle, which actually would end up being what? We could say the area, so the equation of the circle would be what? X squared plus y squared equals to r squared. Now remember, r is a constant, so we could have r in there. Okay, so with that said, what do I do? What do I want to do? I want to solve this guy in terms of x. So what that means is that y squared equals to r squared minus x squared. And that means this implies that y equals to the square root of r squared minus x squared. So in other words, if you come back to this, we're saying for this x value, this is going to have a y value or a radius of right there. It's going to be square root of r squared minus x squared. So the good news is the area of that generic cross section, so the a of x is going to be pi times my radius, which we said is square root of r squared minus x squared, quantity squared. And so that simplifies to pi r squared minus pi x squared. So there's my generic cross section. So now we can go back to this formula. We could say then the volume equals to 2 times the integral from 0 to r times or of pi r squared minus pi x squared dx. Okay, so now we could integrate this. So notice how, and remember, r is a constant. My only variable is x. So this becomes 2 times this becomes pi r squared x minus pi over 3x cubed from 0 to r. Okay? Actually, so then I plug in the upper limit minus the lower limit, so this becomes 2 times pi r. See, if I plug in r here, I get r squared times r, which is r cubed, minus pi over 3 r cubed. And then minus, if I plug in 0, just zeros out. So it'll be minus 0, but that 0 just comes from me plugging in 0 here for x. So the rest of it zeros out. So what does this become? 2 times pi r cubed minus pi over 3 r cubed becomes 2 pi over 3 r cubed. And then distribute the 2, which gives me 4 pi over 3 r cubed. And there you have it. We just showed that 4/3 pi r cubed is the volume of a sphere with radius r. Okay, so once again, just to kind of recap, what did I do? I drew a generic circle, my cross section, and I called it x, and I said I need to find the radius. And the radius of this actually started at the x-axis and ended up on the circle that's centered at the origin with a radius of r. So I said, look, I know the equation of a circle. It's just x squared plus y squared equals r squared. And so once I have that, I solved this in terms of x. And so y, actually, this y represented that length, which started from the x-axis and went to the circle, which is the radius of the circle I wanted. And so once I got that, I plugged it into the equation of the pi r squared, simplified it, and I was ready to integrate it. So the most difficult part of this section is coming up with the generic equation of the cross-sectional area. Okay, once you do that, the rest should be pretty straightforward. Okay, so let's look at a couple more examples, and then we'll basically be done with this. So for example 2, we're going to say find the volume of the solid obtained by rotating about the x-axis, and this is the region under the curve y equals to rad x from 0 to 1. Okay, so once again, what we want to do is I want to basically graph this guy from 0 to 1. So before we actually decide what we're doing, let's just graph this. So 0 to 1, and y equals rad x from 0 to 1, we know looks like this. Okay, so we're closing this off. So what do? I want to grab this and I want to rotate it about the x-axis, which means I'm rotating it this way, right? So if I grab this, and here's the x-axis, I'm kind of using the x-axis and I'm rotating it around the x-axis. So if I rotate this, it'll kind of rotate around and come back, and it'll look like this. And so you could see that the cross sections you want to use, you don't want to use horizontal cross sections, because horizontal cross sections give you like these weird looking parabolas, and we don't know how to find the areas of parabolas, so we're better off taking vertical cross sections, which means if I take a generic cross section, I end up getting a circle again. Now, of course, the way I've drawn this, it looks like this x-axis doesn't go through the center of the circle, but in fact it does, because I'm rotating it about the x-axis. So what you notice is I want the radius of this circle, and once again, I'm going to call this location x. Now, what's the nice good news here? If I were to draw the radius of this, and by the way, I could draw it down to this curve or to the top curve, but I'm going to draw to the curve that I always have the equation of. See, I could draw to the bottom curve, but then to find the radius of the circle, I would need to find the equation of this lower curve, which in this case might not be difficult, but why do more work than we need to? So I'm going to say, look, I need this radius. If I could find that radius, then I have the area of my cross-sectional, sections, and then I could integrate it from 0 to 1. So this radius, since it starts from the x-axis and ends on the curve, is the same thing as just that guy. right? This length is rad x, that length, right? You tell me what x is, and I'll tell you what this length is, which is found by plugging it into this equation. So what we notice is that the area of my cross section is just going to be pi times rad x squared, because the equation of or the area of the circle is pi r squared, and instead of the radius we said this is going to be rad x. So once we have that, that becomes pi x, and the good news is we could say, well, then the volume of that shape, which this solid is going to be. And by the way, why is this solid? Because see, this is solid, and if I rotate the whole thing, this whole thing becomes a solid shape that looks, I don't know, maybe like a headlight or something. So that would be, the volume is the integral from 0 to 1 of pi x dx. And once we actually find the antiderivative, what does this become? This becomes 1/2 pi x squared from 0 to 1. If I plug in 1, I get 1/2 pi minus 0, and my answer is pi over 2. So this shape has a volume of pi over 2. Okay, so it's actually pretty neat what we're doing here. We're finding volumes of these weird looking solids that we would have never been able to without calculus. So I hope you really appreciate what's going on here. Okay, so let's move on to the last example, which this one's a little more complicated. So for example 3, we're going to say find the volume of the region enclosed by y equals to x squared, y equals to x, and it's rotated about y equals to -1. So notice how we're no longer rotating about the x-axis. This one we're rotating about y equals -1. So that's going to change things slightly. But what we need to first do is we need to find what's the region that's enclosed with this guy, and then, and maybe I should say, of the solid obtained through the region enclosed. So they should find the volume of the solid obtained through the region enclosed by these guys. So let's first find where they kind of close up each other. So if I set x equal to x squared, I'm just substituting, and I find out that x minus x squared equals to 0. Factor out an x, and we get 1 minus x, and that means that x equals to 0 and 1. So that's where they intersect each other. So let's draw the picture, because see, the picture is probably the most important thing here. And in fact, if you look at the two examples I did prior to this, without a picture, we're kind of stuck. Okay, so with a picture, what I need to do is, so we have 0, 1, 1. So this is the line, and then this is x squared. So what I'm doing is I'm grabbing this guy, and I'm rotating it about y equals -1. So this is my axis of rotation. Okay, so if I grab this and just rotate it, so what I'm doing is I'm just grabbing this guy and I'm rotating it around. And as I rotate it around, what do I notice? This guy will end up kind of down there, right? Because I'm rotating, and then this is going to be rotated. Now, what do you notice? This is going to have a hollow region, isn't it? Because what you notice is this middle part is hollow because the solid is based off of these guys. So when I rotate this, it's like kind of like this middle part is hollow because there's no solid, but this guy that wraps around it is going to have a solid region. So when you notice, if I take a random cross section, what do I notice? I'm going to get kind of a shape that looks like a donut. And see, this inside circle, that's hollow. Where's the solid part? Right here. So if you notice, when I draw my cross section, this is the solid part. So I want to find the volume of the solid, okay, not the hollow part. So it's kind of like a donut, or the book calls it a washer. So to find the area of this cross section, notice how I have two circles. I need to find the area of the large circle, and I need to find the area of the small circle, which is the hollow part, and I need to subtract it because I only want the solid. Now look at what happens here. when I draw my radius, and once again, I'm going to go up to the top curves because I have the equation of the top curves. I'm not going to draw to the bottom ones because I don't have the equation of this line and that curve. Although I could find it, once again, it's a waste of my time. So what do you notice? The first radius of the smaller circle is that guy. But see, what's the problem? Notice how I start from here and I end up on the curve. However, the equation of the curve, which is x squared, only gives me the distance from the x-axis to the curve. So the radius of this circle, unfortunately, of the small circle, unfortunately, is not going to be x squared, because what you notice is this distance, that much, is x squared. Okay, so but if you notice, if that much is x squared, what's that length? The nice thing is, since I'm rotating it about y equals 1, this distance is 1. So what you notice is that the radius of the small circle will be what? 1 plus x squared. So what we would say is that the radius of small circle is equal to 1 plus x squared. And by the way, hopefully you guys understand, since I'm taking vertical cross sections, because I get circles, everything has to be in terms of x. Now, how would I find the larger radius of this, radius of the larger circle, which starts from my axis of rotation and goes to the line, which once again, what do you notice? This right here, the distance from the x-axis to this line, that's described as x. And then what am I missing? The radius of the big circle is also missing this, but that's 1. So this is kind of messy, but that's 1. So if you notice, if I were to kind of draw out the circle here again, just the washer, just so you see it, what do we notice? This is the x-axis, this is y equals -1. So this radius is found by what? 1 plus x, because that x is from here to the curve, and that's 1. So the radius of the big circle equals to 1 plus x. So now that we have this, the area that I want, which is this region, would be the area of the big circle minus the area of the small circle. So if I were to say, for example, and that's my cross-sectional area, by the way, which is that washer. So what we're going to say is that the area of big circle minus the area of small circle, which equals to, it'll be pi times 1 plus x quantity squared minus pi times 1 plus x squared quantity squared. Okay, and then we could simplify this if we want. We could factor out a pi, and then we could square this, so that becomes 1 plus 2x plus x squared minus 1 minus 2x squared minus x to the 4th. What you notice is these ones cancel out, and I get pi times, what does this become? Negative x to the 4th, and then negative 2x squared plus x squared is negative x squared, and then plus 2x. So that's my area of the cross section. So now that I have that, I just need to go from my lower to upper limits. And what do we say? X equals 0 is my lower limit, x equals 1 was the upper limit. So the volume of this guy would be v equals to the integral from 0 to 1 of the area of my cross section, which is pi times, and by the way, since pi is a constant, I can move it out front. It'll just be pi times negative x to the 4th minus x squared plus 2x dx. And now I could integrate, which would be pi times negative 1/5 x to the 5th minus 1/3 x cubed plus x squared from 0 to 1. And the good news is when I plug in 1, and then if I plug in 0, the 0 cancels out. So I'm going to ignore plugging in the 0 because there's nothing there. So this becomes what? Negative 1/5 minus 1/3 plus 1. And so if I get a common denominator for all these, what do I get? Negative 3 over 15 minus 5 over 15 plus 15 over 15, which leaves me with 7 over 50. So it'll be 7 pi over 15, and there's my volume. Okay, so remember, whenever you rotate something other than the x-axis or the y-axis, you're going to get, like, if it's like y equals -1, you're probably going to have a constant that adds onto it, or you might have to add or subtract something. But when you draw the picture, I think it becomes a little clearer. Okay, so I hope this stuff made sense. Now, once again, you're only going to get better at finding volumes through practice. So remember, the key is finding a generic equation of a cross-sectional area, and then the integration part shouldn't be difficult, okay? But remember, the shapes that you'll mainly deal with, especially when we're rotating about some axis, you're going to get circles. So you're finding areas of circles. Now, there may be other cases where you get squares, rectangles, triangles, but it should be shapes that you know how to find the areas to. Okay, so like I said, from this point on, I mean, we're going to spend quite a few days reviewing this in class, and you're going to be doing certain problems, and so you should be fairly familiar with this. Okay, so that takes care of this section.